Okay. So density is a physical property of a substance. Density is kind of like if you take matter and how squished the matter is, that makes it a high density, or how fluffy the matter is, that will have kind of a low density, okay? And in tomorrow's lab, you're going to be getting the density of, among other measurements, you're ultimately going to be getting the density of two objects. In both those cases, to get the density, you have to, for that single object, get the mass of the object and somehow get the volume of the object. This would be a ratio, otherwise known as a little division problem, okay? So tomorrow's lab might seem kind of simple, but it's to draw you into the process of collecting data the way you need to and working problems the way you need to. So density is how fluffy something is or how dense something is. And in the previous unit, we talked about the kinetic molecular. The kinetic means motion. The motion of all matter. All matter is in motion. And if I were to kind of go here with these physical phases, I would say that motion, does motion increase as you go towards gases, or does motion slow down as you go towards gases? It increases, very good. So motion increases, okay. And usually, and actually water is an exception to this, usually as you change phases from a solid to a liquid and a liquid to a gas, okay, you're increasing the motion, and usually your volume increases. Usually. So for instance, something can stay a solid for a while, and it doesn't have to change its phase from a solid to a liquid, but it will swell as it gets warmer. Okay, it gets closer from a solid to a liquid. Something from a liquid approaching a gas, it swells. Okay, so if that's the case, and density, by the way, you see that symbol there? This is the symbol rho, like you saw on the previous slide. This is density, not a capital D. Okay, if you've learned it that way. Okay, the Greek letter rho, and it's a ratio of mass to volume. So here's the deal. Like this slide says, if volume changes with temperature, you're going to have to specify the density of a substance at a particular temperature. Do you know what I'm saying? Okay, if this is a moving gun with temperature. So a lot of times you'll see like the row of H2O water at 20 degrees Celsius. So we're qualifying it. Okay, so it's dependent upon temperature. So over here on the left, actually we see all it is we have cold. Oops, sorry, go backwards. Okay, we have this ice is cold. Okay, and what do you know about cold water relative to water that's warm?
It falls.
It falls, exactly. And so you're kind of seeing this here. Cold water is denser, more dense. More dense. Okay. The blue, forget about it. The blue is just to kind of show you kind of a little bit of how the movement of the water is. So your cold water sinks, okay? Now, what's that ice, what's this doing relative to the water? What's the solid ice doing relative to the liquid water? It is floating, exactly. So as it turns out, the density of ice is less than the density of water, liquid water. And thank goodness for us, ice floats. Not only does it make it convenient with regard to our tea, but if you think of all of the water associated with the Earth that's tied up as ice sheets, oh my gosh. If those ice sheets would sink and displace that liquid water, we'd be screwed, quite frankly. This over here, this is just a couple of pieces of glassware. And what it's telling you is these glasswares are with regard to volume, liquid, okay? So this is what we call a volumetric flask. It's got one mark, and to that mark it would hold 1,000 plus or minus probably 0.0 or 0.1 milliliters, okay? But my point here is it qualifies it. It says that is the volume of water at 20 degrees Celsius. the 1 liter, 1.00 milliliters. Similar down here, it qualifies it. Okay. By the way, the TD is to drain, and the TC up here that I marked is to contain. I know it's a subtle difference. It's just kind of interesting how they do that. Pipettes, like I showed you in lab the first day, or when we checked in, pipettes, you're counting on draining it. That's what the D is, drain. Volumetric flasks, you're counting on containing it. There's all sorts of little things. So this is kind of a review slide too. We said that there's kind of a yin and a yang to these. You guys told me on your homework there's chemical properties and then there are physical properties. Density, you don't have to do any sort of chemical reaction, so it's a physical property. And then we said there's intensive. What's the opposite of intensive?
Extensive.
Extensive. Very good. And I told you that if you focus on the IN from intensive, kind of take that out, you think of independent. Independent of amount. So density, come back. Density is an intensive property. Okay? Density is independent of amount. So this is to say that I could have, let's pick on ice cubes. You know, I could have an ice cube, like a normal sized ice cube, and it has a certain density. It's a ratio of its mass to its volume. Or I could have a whole sheet of ice. That's probably not a good example because given a large sheet, probably gravity is going to kind of do some things. But a fresh sheet of ice, okay, and it will have the same relative mass to volume as that little ice cube. Same density. Different amounts, same density. So it's independent of amount. All right. So picking on density. So if density is a ratio of mass to volume, we are going to focus a lot on units in here. So units of mass are going to be grams, for sure. Now the units of volume, especially for density, oftentimes units of volume are liters, specifically milliliters for liquids. Okay, so grams per milliliter would be an awesome unit for density. Notice the difference between those two, grams per mil or grams per mil, right? This second one right here, I have taken it and kind of fluffed it out because I want to really emphasize that units of mass are on the top, the numerator, and units of volume are in the denominator. Okay. One more way to write this. Okay. Another way, instead of units of volume milliliters, are units of volume in centimeters. Somebody tell me what is, fill in these blanks. Blank milliliters is equal to blank centimeters cubed. What goes in those blanks? One. One and one, exactly. Okay. Milliliters, centimeters cubed, volume. Okay. What's the relationship? 1. Is it an exact relationship? It is an exact relationship. No uncertainty. Okay. Yep. Okay. So to kind of finish things up, maybe some of you are already familiar with, and I don't do a lot with it, but if something is in the denominator, we can show it's in the denominator by giving it a negative exponent. If it's in the denominator raised to the first power, like milliliters and centimeters cubed, then we give it a negative 1. So that's what that is. Okay, let's do some, all right? So that's what you're going to be doing in lab. Basically taking an object of interest, getting the mass, you're going to put that in the top, getting the volume, you're going to put that in the bottom. Make sure you have units, divide it out. The catch is, quite honestly, that you're going to have to round that thing after, okay? According to the rules that we've already talked about in class. Since we're dividing, are we going to round according to sig figs or decimals? Sig figs, exactly. So let's do this one. Some things are easier or harder to get the volume of. Getting the volume of a block like this is not too bad. So we have the 3 unique dimensions of this block. Okay, and they're all in centimeters, which makes our life easier. Okay, so how are we going to get the volume, given those lengths, width and height? Times them, exactly. And one of the things students are getting used to how to work problems in here, you're going to want to show that multiplication. Even though you're like, I put it in my calculator and just carry it over. No. Anything that goes in your calculator, rule of thumb, write it down. Okay, yep, we're going to get the volume from that, and somebody put on the scale for us, so we have the mass. So it's not too bad. We're supposed to come up with rho. What is the density? Okay, so to get the volume, we're going to take those 3 lengths, length, width, and height, times each other. So I brought my calculator, and I'm going to kind of mirror this problem over here, because I'm going to show you kind of a catch with this first problem. All right. So volume is equal to, and I already told somebody recently who came by my office, but a lot of times I will write down what the calculator displays and what the right rounded number is. So I guess to do this right, I'll do this right. .21 centimeters, no naked numbers. 1.05 centimeters and 0.76 centimeters. Okay, so I'm going to put in my calculator these numbers, and I'm going to write down what it displays. My husband's kind of a smart aleck, so I'll say, I'll write down what my calculator says. And he's like, oh, does your calculator talk to you? I'm like, no. All right. So my calculator displays 1.76358. Okay, that's what my calculator displays. Now we talked about rounding, and I can't justify, let's see, 1, 2, 3, 4, 5, 6. I can't justify 6 significant figures. But before I move on, also I want to, you guys know what are going to be the units? Centimeters cubed, exactly. So here's the deal. What we do to get the number is to multiply these 3 numbers. Okay. What we do to get the units is to literally multiply these 3 units. And so centimeters times centimeters times centimeters is centimeters raised to the 3rd power. We're going to track a lot of units. Okay. Cool. And so this is where, this is fine to write calculator next to it. And I think that this is what the answer says. So can you see why the answer is 1.8? Exactly. There's 2 significant figures here. What, 3 here? And you guys told me I got to round to significant figures. This one is the short chain. Okay, so that's why. You buy that? I feel like I'm belaboring a density problem, but it's important. All right, knock out the density. So density is equal to that mass that they told you, 13.94 grams, divided by, we came up with a volume of 1.8 centimeters cubed. And here's the rub. I put this in my calculator. And I get something other than you're going to see displayed. Okay, I get 1.74 repeating. Let's see, cool. So what would the units be? Almost. Third, yep, exactly. Grams per centimeters raised to the 3rd power. That's it. Oops, I better say calculator. We're not done yet. Okay. All right. So let's see. How many sig figs in 13.94? 4, exactly. How many sig figs in 1.8? 2. Perfect. So how do we got around this? How many sig figs are we allowed? We're allowed 2. So we're going to truncate it there. So how are we going to round it? It'll be 1.7, exactly. And that will be your answer. You good with that? So here's where I get to tell you, sometimes students will want to, and it's not up there, I have to point here. Sometimes students will want to basically carry this volume, the unrounded volume, over for the volume. I say students and actually scientists in general. That's a better number. Taking that 1.76358 centimeters cubed in the denominator is better than 1.8 centimeters cubed. I will tell you, rounding it and then putting it in like the 1.8 gives you a fighting chance of rounding correctly your final answer. But do you see where, well, I'll just tell you that if you go ahead and put, instead of 1.8, if you put 1.76358, you're going to end up with a different number. Oops. Sorry, my bad. This was 7. 7 point, yeah. It's like, wow, that's a really different number. Okay. So if you use the unrounded value, I don't know how to put this, but if you use the mass, same mass, but instead of that 1.8, if you use 1.76358, the unrounded value for volume, rounding it to 2 significant figures, again, is what you're justified because it came from this guy right here. Okay, then your final answer would be 7.9 grams per centimeter. Now, what I usually at this point is I get students, let's say whining. We all whine. I whine. But they're like whining, like, which one is right? Which one do you want? Here's where I say either one is fine. Like, there's a big difference, 2/10. Yeah. Okay, so you can round as you go, or you can round at the end. But you have to round according to the rules we talked about. Okay? And it's my job to catch you on the other side. Okay, so units. When they talk about dimensions and units, they're the same thing. So anytime we work a problem, we're going to track the units, and we're going to see that some units are going to cancel out. If you have the same unit in the top of a ratio and the same unit in the bottom of a ratio, they cancel each other out, and we're going to count on that. Okay. So this idea of letting units do your heavy lifting, there's a lot to be said for that. So I'll maybe pick up on that with the semester. So I mentioned that water is kind of weird, that usually if you take something liquid and you go ahead and you remove the heat, you cool it down, okay, it will shrink. Okay, as in its liquid state, it'll get colder and colder liquid, which water does that. But right about the transition time, about 4 degrees Celsius actually, what water does in preparation, if you're making it cooler and cooler, is to go ahead and kind of fluff out. Okay, about 4 degrees Celsius. Colder than that, and it becomes fluffier. Okay. So about 4 degrees Celsius, it's kind of nice, and actually, if you want to put a little star next to this one, you should memorize the density of water. It's kind of nice. It's got it's 1.00. Could not get any better than that. Okay, so memorize this. The density of H2O, about 4 degrees Celsius, 1.00 grams per mil. Okay, so I had an error already. So this is, notice along the x-axis is temperature, along the y-axis is density. So if we take, and I guess I should point out, you probably already see this, we are from left to right along the x-axis, we are heating it up. We are adding heat. Does that make sense? Degrees Celsius, -8, -6, blah, blah, blah. Okay, so what temperature does water freeze at? 0. Very good. And that's why we got that right there. So notice that as you heat up the ice, what happens to the density?
Decreases.
It gets fluffier. It decreases. That's right. Okay. The density decreases because the volume increases? And the volume's in the denominator of the density. Okay. So right at that transition point, check this out. Okay. It's a phase change. Here we have water that's solid and it's a crystalline, which is kind of weird because of hydrogen bonds. And we'll talk more about that. Because those cute little Mickey Mouse molecules that we looked at before, you know, the red oxygen and the 2 white hydrogens, they arrange themselves in a particular way when they're solid. When you add heat and it liquefies, those Mickey Mouse molecules just kind of fall apart. Well, they don't fall apart, obviously, because there's still little H2O molecules. But the hydrogen bonds just kind of let loose, and the density changes drastically. All right. So we see a similar thing here, which with the density changing drastically at the transition from liquid to a solid. I have quite a few slides here. All right. So density is a ratio of mass to volume. So what that guy's holding are 2 similar volumes, okay? And it just happens to be that so he could close his eyes and without feeling texture, I guess, which one would weigh more? The rock or the styrofoam? The rock, yeah. So the number in the top, the grams, would be greater, even though they have the same volume. Does that make sense? So it's more dense. It's got a greater density. Yep, very good. So here we have 3 substances. We have styrofoam, we have that rock, and in between we have water. So can you see where this is almost like? Can you see that the rock's density is greater than the density of water? Okay, and the styrofoam's density is less than the density of water. That's why it's floating. All right. So we kind of finish up with another ratio sort of problem, mass percent. So the way you get, or I should say, if somebody tells you the mass percent of something, this is what they mean. It's the mass percent of sugar in water, or the mass percent of salt in seawater, right? Some water too, or the mass percent of, you get the idea, oil in chocolate, okay? So there's a component of interest, whether that's salt or oil, okay? And then there's the mixture. So if somebody says it's 50% oil, then that means there are 50 grams of oil in 100 grams of mixture, whether that's chocolate or otherwise. Okay, that's kind of unpacking that percent information. Well, odds of having 100 grams of a mixture are not very good. So this is how we calculate mass percent. And actually in tomorrow's lab, you'll be doing some of this. Kind of lose track of what I choose to do each semester. But what you do is you're going to have a certain number of grams of mixture, okay? You can have like 350 grams of mixture. And somehow you know of that mixture you've set aside, you know the mass of the component of interest. Okay, so you just take that grams divided by the grams of your total mixture. Times 100% to get it in parts per 100. So mass percent and mass fraction are very similar. Okay, you've probably dealt more with mass percent than mass fraction. They differ by a factor of 100. Put another way, you move the decimal over 2 places. Okay, if I go back, check this out. I think I can go back. That's mass fraction. That's mass percent. Mass fraction, mass percent. I could do this all day. To get mass percent, all we did was to take it times 100%. Okay? All right. So let's do a problem. And I usually draw a picture for these things, no matter how small the problem. I think I tell people in drawing a picture, I just get, it buys time. And it makes me feel better about it. So a lot of students don't like to draw pictures, but I do. Because it's like a little story problem. I don't mean to scare you or anything. Okay, so this says that we have added, this is my famous beaker. We have added to this beaker 5.42 grams of sucrose. Okay, and notice we had some water waiting down in there, 28.72 grams of water. Okay, and we're supposed to come up with mass fraction and mass percent. So I think the way I do it in my notes is I'm going to knock out mass fraction and then take it times 100% to get mass percent. So it's not too hard. The problem with this is you have a little bit of addition and you have a division, yeah. Because how are we going to get the overall mass of the mixture? Exactly, add both of them together. And when we go to add these two masses, we're going to focus on sig figs or decimals? Decimals, yep. So that's the only catch to this one. Okay. So the overall mass of the mixture, the thing that's going to go in the denominator to get the mass fraction, is this sum. And you told me I have to round according to decimals. So how many decimals can I carry over? 2. Perfect. This is a really good example because if you went incorrectly with significant figures, you might lose information here. You might lop it off. So now we're ready to continue. That's going to go in the denominator. So ready to go ahead and take the ratio of the mass of the component of interest, 5.42 grams of sucrose, divided by the total mass of the mixture, 34.14 grams. Sometimes students will ask me, well, can I go ahead and put this addition quantity down here in the denominator? And the answer is yeah, that's fine. So now we're dividing. How do we need to round it?
Significant figures.
Significant figures, exactly. How many are we allowed?
3.
3, perfect. Any questions about that? It's our mass fraction. So what's our mass percent?
15.9.
15.9, exactly. That's it. So let me go back to this one. Now, the deal is I mentioned that if you have units, the same units on both sides of the divisor, they cancel. That's what we got here. Okay? So that's why you see on the next slide, we say that mass fraction has no units. There's a lot of things out there that have no units. Why? Because the grams cancel out. Okay. And by definition, if somebody says that your sugar solution is 0.159 mass fraction, then by definition, they're saying in 1 gram of the solution, your sugar solution, you have 0.159 grams of the component of interest, in this case, sucrose. Okay, so that's what I call unpacking. Okay, so you guys told me that with 0.159 mass fraction, the mass percent is 15.9. You're right. You are right. Okay, so these will be due, and we're going to go ahead on to the next part, because like I said, I think it's going to help you. These are density problems, and these are percent problems. Okay. The percent problems, I'll just tell you ahead of time, they aren't my favorite, but I like the Petrucci texts. They're just not my favorite. You'll see what I mean when you got to do them. Any questions? Those are due Friday, yep. And I think we're going to get to that first assignment slide. Interesting. The next part. Okie dokie. It's all about the units. these are some review slides. I know we had this before, and I told you, let's see, memorize, let's see, one big metric prefix, kilo, and commit to memory centi, milli, and micro, if you don't already know. They're the smaller than a base unit. Okay. And which one of these do you need to memorize? Length, the first one, exactly. Okay, so commit this one to memory. You don't have to memorize. Those are what we call, we're going to use them here in a minute, those are what we call equivalency statements. Since I hold my hand up like this, these are equal quantities on either side of my hands. Need to memorize this one? Yeah. Okay. Very good. Okay. So, working problems in physical science, I really believe in working them using what's called the factor label method. Sometimes this is called dimensional analysis. Where dimensions are the units. Okay? So, not so surprising. Whenever, a big part of this is just make sure whenever you write down all your information or the tools at your disposal, make sure you always have the units with those numbers. So, I've been talking about equivalency statements. One of the keys to working problems factor label oftentimes is you have to take a flat equivalency statement and you have to turn it into a conversion factor. So I'll show you, and I'll show you how this works. But for instance, if I say A is equal to B, okay? The 2, that's an equal sign, not a Z. I go like this, and we could come up with 2 unit factors, and I'll show you how this works. But if those 2 quantities are equal, then actually I could come up with a ratio. You see my ratio? Those are equal. That's my ratio. My 2 unit factors are A over B or B over A. Those are unit factors. So equivalency statement, they're like little ratios, right? To a little ratio to use at our will. So then the third, and these aren't necessarily in order, but what we're going to end up doing to get from the given information, what we have, to the information at the end, what our goal is, okay, is basically oftentimes we string up multiple unit factors to get from point A to point B, or C or D, or whatever that is down there. All right, so with regard to length, I bet you guys can tell me this right off the top of your head. So if we wanted to go from feet to inches, 2.5 feet, there is uncertainty to the tens there, okay, so 260. 2.5 feet to inches, how many inches are there?
30.
30, very good. Because you figure 12 inches and 1 foot, and there's 2 of those, that's 24, and a half a foot would be 6, so 24 plus 6 is 30. Perfect. And if I gave you this problem on a test, which I wouldn't, okay, if you just wrote down 30, I'd be like, no, you have to show me how you got there, okay? So 30 is correct. And notice that I'm fancy here, because that's not like the period at the end of a sentence, is it? Okay, why do I have that decimal there? It's not exact, but to show how many significant figures do I have? I have 2, yep. How many significant figures do I have here without the decimal? Just 1, yep. And we had 2 here. So in that simple problem, you'd have to show me how you got there. And in your own mind, I guess it's not really that complicated. How you did it was to go back to, well, I know feet and I want inches. So what do I know about those 2 quantities? And here's what you know about those 2 quantities. Is that an exact relationship? Yes, it is. No uncertainty. Very good. Okay. So here's how I went from the A is equal to B to the 2 ratios, A over B or B over A. Notice that one is the inverse of the other, right? Here's how you do this. So we know that if we have an equality like that, we can divide both sides by the same thing, and we're not messing anything up. So for instance, what if we go ahead and divide both sides by 1 foot? Okay, what's 1 foot divided by 1 foot? What's this quantity? It is 1. Very good. That is the number 1. 1 foot over 1 foot. So, gosh, what is it? Is it the identity multiplicative property of 1? Maybe. But if you take anything and multiply it by 1, what do you get?
Number.
The same number, right. So that's the beauty of taking these from an equality statement into a conversion factor or a unit factor. You can just do it all day, okay? Awesome. Well, we could instead take 12 inches equal to 1 foot. Instead of dividing by 1 foot, we could divide by 12 inches. And then, of course, this goes to 1. Okay, so these things down here at the bottom, these are your A over B and B over A. Okay? Those are the things that we can insert into our problem where we have a bunch of multiplication and it's fair game. We didn't mess with anything. Why did we pick this? Well, because in this problem we knew we were going from feet to inches. So we just didn't like randomly pick something, okay? All right. So here we go. This is our first factor label problem. So we're working the problem now that you got 30 inches from. So I tell students this first term is this is what you were given. Does that make sense? This is what you were given. And this is a conversion factor. Conversion factor. And where did it come from? An equivalency statement. 12 inches is exactly equal to 1 foot. That's where that came from. And I think my builds do this, but can you see? Oh, by the way, I hope you guys are okay when you have terms multiplied. We can have a third, a fourth, a fifth term multiplied by each other. And I'm really a firm believer in writing the divisor there, because then you can clearly see the numerators, and clearly see the denominators. But we kind of think of it as one big divisor. Okay? So if that's the case, what happens to the feet? They cancel. That's the beauty of it. Okay, I know, it's like, that's all? That's all. What units are left? Inches. Is that what we wanted? Yeah. Are we done? Yeah. Okay. Like, I just came up with that out of your head. Why do we have to do all this? Okay. So, just to kind of show you how, if we call this A over B, okay, notice that if we do the whole B over A, which is also a unit factor, okay, what units are we left with if we went with this as our second term? What would be in the top? Feet. Feet squared, right, in the top per inch. So the beauty of writing this out like this is you know that that's wrong. Okay, that's my point. Don't try to put a square peg in a round hole. I don't know. Let's do another one. So the hint for coming up with the right equivalency statement that you're ultimately going to select which conversion factor works for you is you just look at the units. So if you have inches here and centimeters here, what equivalency statement can we use? Exactly. No pun intended. Exactly. Yep. So let's knock this one out. So what's our first term going to be? The centimeters, yeah. 5.52 centimeters over 1, exactly. Very good. Oh, I forgot to do this. So you can jot this down if you want. But working problems, oftentimes I'll kind of show you the flow of the problem. So here you see how to accomplish centimeters to inches is what you told me, that 1 inch is equal to 2.54 centimeters. All right. Yep, you told me the first term's going to be that 5.52 centimeters. Perfect. So we're going to use this equivalency statement, and we're going to put one over the other, and we want units of centimeters to cancel. So what number is going to go in the bottom here?
2.54.
Very good. 2.54 centimeters. What number goes there? 1 inch. Perfect. You got it. So doing it this way, what cancels? Centimeters. Yes. Okay, now our calculator is going to display something. But before I show you the rounded answer, how do I need to round this answer? Hold up numbers. Hold up. Yep, I'm liking it. 3 sig figs. Perfect. You're done. So with regard to length, we have gone from the metric to the English system. Okay. So just be sure you show all your work. Let's do another one. And I'm wanting to say that this is one where I have it worked 2 different ways. Okay. Do you have to memorize between ounces and grams? No. I don't have it memorized. Okay. And I'll tell you, you have to show all your work, but honestly, you could go to the Google right now. I don't know if Siri knows, but Google would know. You can just say, type it in that question, and it will tell you. Yes. I think you're right. I think you're very close. And there's a couple ways to skin this cat. Notice that I've chosen in doing this for you to go from, instead of going straight from ounces to grams, I'm going to go from ounces to pounds and then pounds to grams. Okay. So, is there uncertainty? Is there? That's a question mark. Any uncertainty there?
Yes.
No, there's not any uncertainty. Why is there no uncertainty? Because that's how many, the English folks, us, we set it up as that's how many ounces are in a pound. That's by definition. Is there any uncertainty here? Yes. Yes. So what's our first term going to be? Have to go back to the previous slide.
Ounces.
Right. It's going to be that number we need to convert, the ounces. Yep. 2.75 ounces. All right. So how do we get ounces to cancel? What do we put down here? 16 ounces. Very good. And 1 pound there. Does that make sense? Cool. So you can kind of cancel them as you go. Okay, so we're left with units of pounds. Notice I'm like ignoring the numbers. I'm just blowing them off. So we're left with units of pounds. And so what goes down here? 1 pound. Very good. And what goes up here?
Grams.
Grams. Yep. From that equivalency statement. Perfect. And units of pounds cancel. We're left with units of grams. So unit-wise, I'm done. Like, hey, wait, we don't have a number there. But, that's how things work. So we're going to round the number here, but let's count sig figs. So how many sig figs? Oops. Almost 77. How many sig figs in the first term? 3. And do we need to count sig figs here? No, because it's exact. Now this is where, this is the first time we've run into this. You guys told me that there's uncertainty with that digit, and there is. How many sig figs in 453.6? 4. Yep. There are 4 sig figs there. Okay. Now here's where I get to kind of say, when they do this right here, that equivalency statement, they mean exactly, I can't spell exactly 1 pound will weigh approximately 453.6 grams. Okay, so there we don't count the 1. That's the way I think of it anyway. Okay. All right, so how do we need to round our answer? Oh, it's already up there. So you see why we rounded to. How did we round it? Because of this guy over here. So here's why I wanted to make sure that I got this far. There's just another example. Another example. Oh, no, I guess I'm going to have to, it's clear down here, you guys can see in your notes. Let me look at those. I think I'm going to assign 127 and 128, but not all of them. So just hold your horses. I know, I'm just kidding. So here's the e-text. Wake up. Not you, the computer.
I ain't gonna wake up.
Oh, it timed out on me. Let me just double check. 27, 28? I think these ones guys are good for that. Yep, so just do 27 and 28, okay? So that'll be Good Friday also. And don't worry about the other two problems. Are there any questions about that? What's this one? I'll push it out there on the Twitter feed. Let's see. So in addition to the other 4 problems, these are also due Friday. All right? Cool. See you then. If not before. Wait, we have lab tomorrow.